Hello everyone. In our lecture series based on vector analysis, we have done scalar product of two vectors, we have done vector product of two vectors, and we have also done scalar triple product and vector triple product. We understood the properties and we also try to understand using example the whole concept. So today we are going to discuss scalar fields and vector fields. Scalar and vector, they hold the same meaning. Scalar is a quantity which has magnitude only, and vector is a physical quantity which has both magnitude as well as direction. So if we have any physical quantity, you talk of mass, temperature, pressure, force, there are so many quantities we all study in physics. There are so many physical quantities. So if we can express a physical quantity as a continuous function of the position of a point, suppose at a particular portion we have some point, and we can express physical quantity as a continuous function of position of a point in the region of space. So in a particular distance, if we can explain that particular quantity, then that function, because we will express the quantity in terms of a continuous function. Let this be a physical quantity, some physical quantity, be it temperature. We can represent this physical quantity as a continuous function of the position of a point in the region. So this is a region, okay, this is a region particularly, and we have considered a portion where we say that there is effect of that physical quantity. So basically we are representing the physical quantity with a dot, and then we are saying that in a particular region the effect of that physical quantity will be there, will be felt and will remain the same. So we can express that physical quantity in the form of a continuous function. See, either we have a discrete function or we have a continuous function. When we talk of region, some space we have to cover, then we always talk in terms of continuous function. See, something, if we have something which is covering a particular portion like this, like this, so then we say that this is done by some discrete function. Why? Because this is having some discrete values, some particular values. So this would be determined by some discrete function. So we say like this. But if we have a particular space and we want to cover the entire region, we don't know whatever values are there. We are saying that in whole of that region, the same physical quantity is there and there is no change in the value. The value is also same, but that quantity is spread over some distance. So if we want to show the spread, just like this, if we want to show the spread that okay fine, that physical quantity is over this particular region, then we talk in terms of continuity, because this is continuity. We are not counting. See here, I can count, this is 1 2 3 4 5 6 and so on, but here I just can't count. It's just spread out. So here the physical quantity is spread out over this region, this particular region. And to express it, I need a continuous function. Continuous function of what? Of position of a point. Obviously, I would consider some point, that let I consider this particular point, and then I will simply integrate it over the entire region. Suppose this is the length 0 to L. So I will integrate this function, this point. Suppose this is f of x, where this x is position. So I will simply integrate it over the entire length. This is the meaning. So we are not talking in terms of discrete values. When we talk about region, when we talk about space, we can't differentiated, we can't divide it into segments, that you have a ground suppose and you have divided it into lots of segments. This is not possible. In that case, we just consider the whole region as such. And this is the reason why we say that we can express every physical quantity as a continuous function of position of a point. Obviously, we need one point and we will see its position. Okay, so this is, we have taken this point and its position is x. We will represent this point in terms of a continuous function of position of a point in region of space. So this is the entire region, this green band, and we have considered this particular point as a continuous function of position. So this function, such a function, is called a point function, since we have defined a function of a point. We had a point and we have expressed it in terms of a function. So such a function is called point function, and always it is a continuous function. All we have to do is we will simply integrate it. If we want to find any value, we will integrate, not differentiate. Differentiation is when you have discrete values and you can actually differentiate. But integration means that in continuity, you know the one value and you will just integrate it over the entire space, over the entire region. All you need to know is just the limits. What is the starting limit? What is the ending limit? So region of space in which it specifies the physical quantity is called a field. So this whole region of space, now as I'm saying that this particular fx, this function is there, this point function is there, and this point function is spread over this entire place. See, this entire region is covered by this function fx. So this entire region is covered. So it's not that only at this particular point we have fx, even we have fx at here also, we have fx here also, and everywhere it will be having same value. So it is distributed over the entire place. So the region of space in which it specifies the physical quantity, or the region of space in which the effect of that physical quantity is felt, then that is called a field. Okay, so this is a physical quantity, and if we define it in terms of a continuous function of position of a point, this is a point, so this particular thing is your point function, and this is actually spread over this entire region. So this particular thing, this region, this is called field. Wherever, like if this is your point function, so everywhere you will experience the same function. Everywhere you will experience the same quantity. So if we are talking about that this temperature, this is a temperature, this point function is temperature, then everywhere we are saying that around this particular distance or in this specific region, we will be experiencing the same physical quantity, that is temperature, and its value, everything will be same. So this whole region is called field. Field means this is field of this point function. Now if point function is here, standing here, then this whole region is its area, its territory. So everything inside here belongs to this point function, and everything inside this region is basically this point function. Okay, so this is the concept of point function and field. So we have a point function and the area around it where its influence can be felt, that is called field. Now there are two types of field. One is scalar field and other one is vector field. Now let's study scalar field. Let's talk about scalar field first. Simply, scalar field means the field around a scalar. And if we talk of vector field, then that is field around a vector. This is the definition or understanding in a simpler way. Suppose this particular thing is your scalar, then this whatever we are showing, this is basically the aura of a person. Aura is something, the region around a person where the energy of that person can be felt. So if this is a scalar, then this particular region is its scalar field. We can experience this scalar in this entire region. So scalar field is defined as the region of space. Obviously, it is a region in space with each point of which there is associated a scalar point function. So whatever is this scalar, it is the same over all this region. Okay, this basically pic is simply, it's just an analogy to understand what it is, that if you consider someone, whether it is scalar or vector, and there is a field, be it a charge. We talk of charges and we say that there is electric field of a particular charge. So this is also the same thing. Even charges, they are also a sort of scalars. They don't have any direction. So if this particular picture, the man in this picture depicts a scalar, and this is basically a charge which is a scalar quantity, and then the area around this charge, we can experience its electric field. We know that around the charges there are electric fields associated with it. That if you bring, suppose this is a positive charge, and if you are bringing negative charge, so if it comes closer, it will suddenly feel a very strong attraction, force of attraction, because here in this particular region everything is positive, everything is positive. So if one charge is present, the whole region around it, its field would be positive, so it would be representing some positive electric field. And then whenever a negative charge comes and it reaches up to here, then suddenly it would feel a very strong force of attraction, because in this entire region the positive charge is spread. So this is the field of positive charge. Similarly, if a positive charge is coming, so it would repel it. So the moment it comes further closer, the moment this charge comes closer, it would suddenly feel a very strong force of repulsion, and that would just, it would just push it away. So one charge is there, and we represent any scalar quantity as a continuous function of position. Obviously position is there, and then the field around it is considered to be its field. So if it is a scalar, then field around it is scalar field. And obviously we say, like, this definition is more scientific definition, that we are not saying it simply that field around a scalar is scalar field. We are saying that it's a region of space with each point of which there is associated a scalar point function, because after all, whatever it is, we denote it, whatever physical quantity is there, we would express it in terms of a function, a continuous function which is known as point function. So the examples of these scalar fields could be pressure distribution in atmosphere, or it could be gravitational potential of system, it could be electric potential of system of charges. So basically anything which has magnitude only but no direction. Whenever we talk of electric potential of a system of charges, we are not concerned with direction. Similarly, temperature distribution. Now this figure, this earth is there, and this picture depicts the temperature distribution. So you can see that a particular color actually tells us or gives us a particular temperature. So you can see that this blue region, that would be having some particular temperature, some colder one, and then this particular region where it's all orangish red, then that is some hotter temperature. So now all these, basically you can say that now temperature is what? Temperature is scalar. And you have determined, you must take a point somewhere, you just take a point and just term it, say it is a point function, but everywhere, and this whole region is its field of this scalar point function, because everywhere you will experience the same temperature. Whatever temperature is here at this particular dot, same temperature is spread over this entire region, whichever is in reddish orange color. Similarly, here you can see the blue color. So whatever temperature is at one particular point, everywhere inside this region, same temperature is there. So this is the field of that temperature. If you consider one particular point, then you would say that this whole region, this whole blue colored space is the field of that particular point. So everywhere you will find the same thing. In a particular region, in the field of a scalar quantity, in the field of a point function, you will find the same point function everywhere. Okay. Similarly, you can see here that we have green region, you can see here. Of course, that also denotes some particular temperature. So whatever temperature is here, same temperature is here, same temperature is here, same temperature is everywhere in this region. So to find out the temperature of this particular region, you can find the temperature at one point and simply integrate it over the entire region. And this is the meaning, and this is the field. This is the scalar field, because everywhere you are going to experience same temperature. Everywhere you are going to measure same temperature. Alright, so this is scalar field, and mathematically we can express a scalar field as phi is equal to phi of xyz, or we can write down phi is equal to phi of r vector, because we know that r vector comprises of xi cap plus yj cap plus z k cap. Whenever we mention r vector and it is a vector representing three-dimensional space, so we often write it as this. This is the general way to express a vector. So we just simply mention the x, y, z components, the components of the vector, because if we are talking of scalar, scalar has nothing to do with direction. So here this I cap, j cap and k cap, they tell us the direction. I cap tells us that we are talking about x axis or x direction. J cap tells us we are talking of y direction. K cap tells us that we are talking of z direction. But these x, y and z, they give us magnitude. They only tell us the number, that how much, what's the quantity, how much in x direction, how much in y direction or z direction. So that's why to express a scalar field, we are only concerned with the magnitude, because scalar quantity is a quantity which has magnitude only. Okay. So either you write the vector in whole, or I think this is the better way to express just by considering the components. And this phi is a symbol for physical quantity. This physical quantity could be temperature, it could be density, anything, any scalar quantity we can consider. Now linked with the scalar field, we define a term called level surface. Now what are these level surface? So the definition says that in any scalar field, so this is particularly for scalar field, okay, where the magnitude is the same in the entire region, magnitude is going to be same. So in any scalar field, we can draw surfaces corresponding to same value of scalar physical quantity. These surfaces are called level surfaces. Like on the same level, each and every surface is on the same level. That is the value at each and every surface that we are going to make corresponding to the scalar field. The values are going to be same. So all those surfaces are basically identical surfaces. That's why we call them level surfaces. We can draw surfaces corresponding to same value of scalar physical quantity. Whatever physical quantity we are studying, be it temperature, be it density, anything, it's just that in that particular region where we are observing the same physical quantity, where everything being measured is the same value. If we are talking about temperature, so and we have considered one particular region, and in that entire region the value of temperature is same, we are getting same physical quantity, so we can draw surfaces corresponding to that region. So here you can see here that this is equipotential surface. You must have read this in the electric field and charges chapter, that this is a positive charge and all the fields, we know that electric field lines emerge out of the positive charge. So we can draw is surface. So everywhere the value is going to be same. The value of the charge experienced, like if this is the positive charge and we are saying this red dotted line represents the field of this positive charge, now obviously it is a scalar field, so we can draw any surfaces. So all these surfaces basically, this this innermost red dotted circle and then this outermost the outer one and then the other one and this outermost circle, all these circles, everywhere the value of this positive charge is same. Suppose this positive charge has magnitude 2, we say plus 2 q is this. Okay, this charge, suppose this is a positive charge, so plus 2, you can write down q as the charge. So now at this particular surface, this smallest circle, whatever we experience is plus 2 charge. Then at this point also plus 2q, at this point also plus 2q, at this point also plus 2q. So everywhere, so we have drawn surfaces. We had just this particular positive charge and we knew that this outermost circle till this region, in this entire region, if I just highlight it, this entire region is the field of this charge. This is a scalar field. And now in this scalar field, we can draw as many surfaces as we like, as we want, corresponding to same value of scalar physical quantity. So here all these surfaces drawn with dotted red lines, they represent the same quantity, that is plus 2q charge. So these are level surfaces. Now here you can see this particular, here this is for isothermal surfaces. We have drawn isothermal surfaces. You can see these bars, these simply, they all represent some values. These particular bars have been drawn, these all, just let me draw it properly. Here you can see that this whole setup that's been made up of lots of surfaces. Basically you can see these steps. So all these steps, they show different surfaces, and in this particular region where we have this orangish red surfaces, so these are isothermal surfaces. So at this particular region, in this particular region, we will be having same temperature. So everywhere, this whole, the temperature is going to be same, this region. So these are the isothermal surfaces. We can draw as many surfaces as we like in this particular region because all will be corresponding to same value. Similarly, for other colors we can show. Then here if you come, this is for equidensity. These are equidensity surfaces. So everywhere the density is same. Okay, density is same. So we call them equidensity surfaces. So if you see these fine lines, basically they all represent surface. These all lines, they represent surface. So these are also equidensity surfaces. Corresponding to particular density, we have divided the whole region into surfaces, into number of surfaces. So all these are called level surfaces. Similarly, this last example you can see, this is for pressure. So we call them isobaric surfaces. Okay, this was isothermal surfaces. Then this, for charge we had equipotential, for density we had equidensity, and this is isobaric surfaces. So now you can see that there are regions of different pressure. So here in this particular region we are having almost same pressure. So that's why they have divided this region into lots of surfaces. So you can see there are so many surfaces being drawn. All these are level surfaces, and if scalar quantity is pressure here, so we call them isobaric surfaces. So all in all these surfaces, they are level surfaces in general, but then it depends on the and on the quantity itself. Whatever physical quantity you have, then you can give them special name. The most important fact is that no two level surfaces corresponding to different values of scalar point function can intersect. So whatever is the function, see, function for a particular if you are considering, then that function would integrate over the entire region. Okay, so we would be having some different limits. So we can say if this is a circle, we would say from 0 to r, the integration would be from 0 to r if r is the radius, whatever the function is, fx dx. So whenever we draw two level surfaces, they would be having different limits, because this innermost circle would be having limit from 0 to say some distance x, the another one would be some distance x2, x3, and so on up to r, where r is the greatest distance of all. So whenever we draw these two level surfaces, so no two level surfaces corresponding to different values of scalar point function can intersect. You can see here we have drawn so many surfaces, we are seeing so many surfaces, but none is intersecting. So this is the rule that no two surface should intersect. Why? Because then at the point of intersection, suppose you have two surface, and this is, if you are getting, otherwise this is the ideal case, that you have drawn two surface and they are not intersecting. This is the ideal case, but this is the non-ideal one. But if it happens, then you can see that you are getting 2 points of intersection here and here. So if you are getting 2 points of intersection, that means there are two different values. So they would say that they would imply that the function is having different values, that function is assuming two different values, which is not possible, which is in contradiction with the assumption. And what is the assumption? We always say that scalar function, whatever it is, it has same value throughout. We always say that this phi r is a single valued point function. So this is very important point. Similarly, when we talk of the electric field lines, when we study the charges chapter for the first time, when we study the electric field lines, the same point is there also. We say that no two electric field lines can intersect each other. The reason is same, because if they will intersect, that means we would get two different points, and that means that there are two different values. But the field is of a particular charge. So if we are talking of one particular charge, that means one particular charge is present there. Then how can we have two different values? Whenever we talk of a scalar function, it always carries single value. It is always a single valued point function. So whenever we can draw as many surfaces as we like, but the only condition is that those surfaces should never intersect. So these level surfaces, they never intersect. This is an important point. Now let's discuss the vector field. Let's talk about vector field, the region of space in which a vector quantity has unique value. Now that unique value includes both magnitude and direction at each point is called a vector field. Obviously, when you have a vector, the space around which you can experience the force or the effect of that vector, that is known as its field. So the field around a vector is vector field. So thus, in that region, everywhere there would be same value. So that vector quantity would be having unique value. But now, unlike scalar, there would be both magnitude as well as direction. So same magnitude everywhere and same direction everywhere. Like all the vectors, they should be pointing in one particular direction. Now this is the thing. In scalar, there is only magnitude, so we say that everywhere the magnitude is same. Same value should be there in that particular region. But when you talk of a vector, then magnitude is definitely the concept, but direction is also there. So then we say that all the vectors, they should be having same magnitude and they should all point in the same direction. So if that happens, that particular area is called a vector field. So here this figure, this indicates the wind pattern. Now wind is moving, and of course we always say that we measure the velocity of wind. We say that whether wind is blowing really fast or slow. So the magnitude is definitely there. And then we also talk of the direction, in which direction it's moving, whether it's moving from east to west or west to east or north, south, any So whenever we talk of the wind, we talk in terms of magnitude as well as direction. That's important. So any particular region, like you can say this particular zone, all the vectors, they look alike. And you also know that we often denote the magnitude of vector by the length also. So if we have these two vectors, so this has larger magnitude, we often denote the magnitude of vector by making it larger or smaller. So the length of the vector, the length of the arrow determines the magnitude. That also tells something. Everything in physics, all the symbol, they say something. Everyone has a story to say, to tell. So larger magnitude means bigger arrows, larger arrows, and the smaller arrow, though arrow is there, but that tells us that this is having smaller magnitude. So here in this region, this light peachish region, you can see that all the vectors, they are of same size, so that means the magnitude is same, and they all are pointing in same direction, so that means direction is also same. So this is a vector field of the vector quantity, and here vector quantity is basically the wind. You can see all these colors, they depict that zone. You can see the green portion. Wherever you can see the green portion, you would see that the direction is almost the same of the vectors and the magnitude is also same. Then the blue zones, all these are zones. So all these are vector fields. So if I have to just show, then this area except this green, so this area also represents a particular vector field because here all the vectors, they are of same magnitude and same direction. So same physical quantity is here. Similarly, if I talk about this green zone, this pattern, then here also the things are same. So basically the meaning is same, that field basically is the mirror of, of the quantity. It tells you what kind of quantity it is. If you take a point and you have a field around it, its field would be showing the same behavior, same characteristic of that physical quantity that we are talking. And then we can express vector field also mathematically. So the way of representation is almost same, but the only difference is here you can see the arrow. On both sides you can see that the quantity is being written with an arrow overhead. And again xyz component, because vector wants both things, both magnitude as well as direction. So this arrow does the work of showing the direction, and then xyz are again for the magnitude part. So you can represent it, and a is symbol for any vector quantity. So all those vector quantities which have both magnitude as well as direction we can use. For example, wind velocity, then there is electric field, magnetic field, gravitational field, velocity of a moving fluid at any point, electric force per unit charge. So everything which has both magnitude and direction, we can use them. So this was all about scalar fields and vector fields, and in the upcoming video we'll continue with our chapter and we'll start doing more mathematical part now, because this was all about the basic info of vectors. This was all the theoretical stuff that we study in vector analysis, and now afterwards all the videos upcoming, they would be dealing this chapter with this chapter mathematically. So we will be doing some derivations, we will be learning formulae and so on. So please subscribe to my channel and keep watching the videos. Thank you.